Hello everyone, this is Samuel and here with me is
Joel.
we are making this presentation for our deep learning project which is predicting solar power output using deep learning algorithm. I will start with the motivation for the project. One is climate change. Climate change has been on the rise for the past few decades and the effects are well known in the community. And the major sources of electricity such as fuel, coal, crude oil sadly contribute to climate change and also to greenhouse gases emission. So the alternative to this is using renewable energy. The carbon footprint of renewable energy are actually very low, and that of coal is about 16 times of that of solar power. So this has led to an increase in the use of renewable energy over the years in the electric power system. However, renewable energy sources are variable energy sources. They provide intermittent power as the sources of this power are greatly affected by weather parameters such as sunshine, temperature, radiation. So this makes it very difficult for electric grid operators to sort of balance the electric power system as power supply must be equal to the power demand plus losses along the line. So being able to forecast the future production will greatly assist in minimizing this problem.
And the dataset we used for this project was downloaded from Kangoo, and it describes the system production of solar plants alongside the weather pyramids. The shape of the dataset is uh, 8,760 and 7. It contains 7 variables, 6 of which are independent variables and 1 dependent variable. And the system production vary with the 6 dependent variables. And it contains 8,760 data points, which one hourly data for a year of the solar plant, and this data was recorded from January 2017 to December 2017. And the dataset didn't require much pre-processing as there was no missing values or not valuable values. Um, we also explored the correlation between the variables. The radiation and the sunshine had the highest positive relation, which signifies direct relationships with system production, and the ones with negative values signifies an inverse relationship. Here we have the daily production, and we can see that the peak happens in the afternoon. Also, from the diagram, we can see that the spring and the summer months have the highest production. We applied a min-max scalar normalization, and we also split our datasets into 70% trend data and 20% validation data and 10% test data. These diagrams are the daily plots of all the variables, and we can observe that radiation, sunshine, and system production follows almost the same curve, which shows high correlation.
So what are we trying to solve? The data set is a multivariate time series data which contains multiple variables. So we are going to forecast our target variable based on all other variables. So given that we have y equals to y1, y2 up to yt, where y1 is the input matrix of the first variable, in this case let's say temperature, and also yn is the input matrix of the nth variable. So we can compute our input matrix to our deep learning model as x equals to y1, y2 up to y of t, where t is the number of time steps. In this case, we have 8,760, and n is the number of variables, which is equal to 7, and h is our horizon of interest, which is 1 hour ahead. So what we did first was to identify our features and targets for our deep learning models. Initially, we dropped the variables that had almost zero correlation with the target variable, but it actually had no effect on the performance of the model. The features are lagged values of all variables, including the system production itself, and the target variable is the feature value of the system production. We transformed our data into a 3D tensor of shape with batch size, time steps, and non-F, where time step is the number of lagged values or window size. And in this project, we are going to be using 96 hours of lag values to predict the 97th hour, which is the next 1 hour. And you can see that when we did the trend shape or the validation shape. So we used 3 different models to make forecast and then compared the result. Our first attempt was using LSTM, and LSTM are variant of recurrent neural network. They solve the gradient vanishing issues with RNN. So LSTMs are able to remember long and short term information. The flow of information in the LSTM network is controlled by 3 gates. First is the input gate, which determines data to be carried from the previous state to the next state. We also have the forget gate, which decides how much of the previous data will be forgotten and how much of the previous data will be used in the next step. For example, using this equation of the forget gate here, this equation here, we can see if the calculation needs 1, it means that it would use the information in the next or current step, and if it yields 0, that means we forget the information. The output gate also determines the information that will be taken to the next state. We also used the 1D convolution convolutional neural network, which makes use of a one-dimensional filter, unlike the image classification where we use two-dimensional filter. Here in this case, we use a 1D filter or a rectangular filter. And in the case of CNN, the normal CNN, we use a square filter. And we use this filter to extract features from the data sequence. And our third model, we use the CNN LSTM model, where CNN is acted as the feature extractor, and we use our LSTM as the predictor.
And the STM contains 3 layers. We also use 2 dropout layers and a full content layer, and we use the ReLU activation functions. We try to improve the model complexity. And then the 1D convolution, uh, it has 4 convolutional layers with no pooling layers and also a fully connected layer. We also use ReLU as our activation function. Then the 1D CNN and CNLSTM model is a combination of the last 2 models. We extracted the 2 models together.
So in our result, all our models actually are underfitted, and one of the known causes of underfitting is regularization. So we did try to remove the dropout layers from all the models, but it had no effect on it. Didn't The underfitting was still there, and we also tried to increase the model complexity by adding more layers and more changing the activation function from ReLU to an age, and also reducing dropout layers, and it actually had no effect, and we actually got more bad results. And this is the result of uh, one of the forecasts using the LSTM model. You can see that this is not really good. And challenges and future work is that one of the challenges we had with the model is underfitting, and we look to explore more means to tackle underfitting. And also data set contains just a year value. So we are looking to explore data set that contains actually almost at least 2 years value, because when you divide data set into seasons, we have spring, winter, spring, summer, fall, and winter. Most of the training data sets were actually values from summer and spring, while validation was like for fall and winter, which had like literally no value used for testing. So we're looking at getting more data sets, and also we also look to explore more data processing, and also use better models like transformer based models on the same data set or in data sets. And also this has been a good learning curve for I and my partner here, and this have made us to learn more, and also we'll be looking to dig more into the field of deep learning. So now we go to the code demo. The code demo. Sorry about that. So first we import all necessary libraries, and we also set seed for uh, to get the same results. One of the issues we faced was that anytime we run our code based on the same parameters, we actually got different results. So we had to set seed, and that actually stopped. Then we extracted the data set, and this is the data set. You can see the shape here. It's 760 by 7, and we also checked the information of the data set, and we could see the number of values in each column, and the type of each of the variables. Then this is to show the count, std, mean, and the maximum value of each of the variables, and there are actually no outliers in the data set. We also check for non values and also null values, and there was uh, none of that. We also explored the data to visualize data, and this is a day data. As my partner said before, we could see that the system production has like a similar curve to radiation and sunshine, which shows like a very strong positive correlation. Then this is the full data set for a year. We also explored correlation, which shows the correlation between all the variables, and we can see for each of the variable, the correlation between the variable and itself is actually it's always one. You can see wind speed to wind speed is one. Then wind speed and sunshine, is like 0.12. We can see that radiation has the highest correlation of 0.79, followed with sunshine of 0.56. We also resampled our data to daily data just for our exploration, and we can see the daily plot of all the variables. We also sampled it for monthly data, and this is where we're able to know that spring and summer months actually have the highest production, and winter and fall are almost close to like no production. Then next thing we did was to normalize our data. We explored different normalization, because our data contains a lot of zero values, because in the night there's no production, and also early in the morning there's no production. So we actually opted for minimax scalar. Then we also split our data set into 70, 20, 10 for train, validation, and test. So we have 1133 for train data, 1752 for validation, and 875 for testing. So this code here actually converts we use it to extract our features and our target. So in this for time series modeling, the feature also contains the target variable itself. So it contains the lagged values of the target variable. So we our window size, which is the number of time step while looking back into the data set. We used 96, and the horizon is 1 hour. That means we're forecasting the next 1 hour, which is in 97th and 7th hour. So our input shape, we also explored using hyperparameter tuning to find like the best hyperparameter values for our model, and this gave us a value of values of um, of 32, 32, 32, 16, and the best adaptation function is ReLU, dropout 0.2, and also the linear rate to be 0.01. Then we built our LSTM model. Like I said, we were experiencing seeding issue, so we had to seed like almost all blocks of the model. And for the for the LSTM model, we had a total number of parameters of almost 500 or 500,000. Um, we use Adam optimizer as our optimization function, and the loss function of mean squared error. So we compile our model. We also use the model checkpoint to save the best model during training while monitoring the validation loss. And we also save the best, so only save the best only to true. Then we also use early stopping, and actually here, because our model is underfitting, we're actually studying the loss and not the val losses. So we ran our model for 50 epochs, and we used the backside of 16, and it came to completion around the ninth epoch. Now you can see that our model actually is underfitting because the training loss is more than the validation loss. Then we loaded the best model back that we saved during training, and we use that to predict our uh, using S-test to predict get our Y prediction. And we also converted the Y prediction and the text actual into a pandas data frame, so we could compare. Like I said, most of the values actually contained 0, because in the morning there's no production, early in the morning rather there's no production, and late in the night there's no production. And this is this is a plot of our result with the prediction. So the text, the red actually is the original, the S test, while the one in blue is the Y prediction. So we also compute our mean squared error and also the root mean squared, and these are the values we got for using LSTM: 0.02, 0.002, and 0.0449.
This model is a 1D convolution, and we contain three, four 1D convolution layers, and we use the value as activation functions, and we try find the we have 100, 140, 1000 something per first, and we use optimize the ADM and use the loss as a mean square error, um, and we
So after that, we ran our model for 50 epochs and a bucket of our system, and it usually stopped at the 12th epoch. And also, this also was underfitting, and we also tried to remove dropout layers from from um, from the model, and it has no improvement. Also, we removed the maximum pooling layers, and actually improved the model. So this is our prediction against the text actual, and this is the curve again. The red signifies uh, the text actual, and the prediction is the one in blue. Then this is the mean squared error, and we can see that the root mean squared error is actually higher than that of the LSTM, which means LSTM performed better than this 1D convolution. Then lastly, we combined both layers of the LSTM we built initially and also that of the 1D convolution layer. We also use Adam optimizer and mean squared error loss. We also save the best model using model checkpoint, and we also employed early stopping. And this actually took a lot of time to train, I guess because of the number of parameters, which is slightly higher than both of the LSTM and the 1D convolution. So we also used 20 epochs and a batch of 16. So we have this curve here. It's also under was under fitting, and we had our prediction here, which is uh, very close to zero. And this is the curve of the test prediction against the test actual. And we can see that also that the CNN performed better than both of the previous models. And this is where we compared all the loss plots of the three models. This for the LSTM, for CNN, and also for uh, CNN and LSTM. Thank you very much.
Thank you.